Hello everyone. In this video I shall be discussing the factors affecting the rate of nucleophilic substitution reactions covered in previous videos. As stated in previous videos, the main steps that occur in a nucleophilic substitution is the attack of the nucleophile on the partially positive carbon bonded to the more electronegative halogen group. The nucleophile donates a pair of electrons to form a dative covalent bond, while the carbon-halogen bond breaks heterolytically, and the halogen gains both electrons in this carbon-halogen bond to form the halide ion. Four factors affect the rate of nucleophilic substitution. The first one being whether the halogenoalkane is a primary or tertiary halogenoalkane. The second depends on the identity of the halogen group or the leaving group. The third depends on the identity of the nucleophile attacking the positively charged carbon. And the fourth one would be the choice of solvent used in the reaction. I would start with the first one. The first one states the first factor depends on whether it's a primary or tertiary halogenoalkane. Primary halogenoalkanes undergo SN2 mechanisms, which is a one-step mechanism that involves the transition state. On the other hand, the tertiary halogenoalkane undergoes SN1 mechanism, which is a two-step mechanism and involves the formation of a carbocation intermediate. The formation of a carbocation intermediate, or in terms of the stability of the carbocation intermediate in comparison with the transition state formed for SN2, the carbocation intermediate is always more stable than a transition state and thus requires less activation energy for its formation than a transition state does. Therefore, the activation energy required to form a transition state is higher than the activation energy required to form a carbocation intermediate. And thus, if both reactions were carried out at the same temperature, the tertiary halogenoalkane, which forms a carbocation intermediate, would be the faster rate of reaction. Therefore, as stated here, SN1 mechanisms have a faster rate of reaction than SN2 mechanisms, and therefore tertiary halogenoalkanes always react faster than primary halogenoalkanes. As for the second factor affecting the rate of nucleophilic substitution, which is the identity of the halogen, identity of the leaving group. The identity of the leaving group affects the rate of reaction in two different ways, which contradict one another, but one's effect is more dominant over the other. In terms of the electronegativity of the halogen group, the more electronegative the halogen group is, the more positively charged this carbon atom in the carbon-halogen bond is, this electrophilic carbon, and thus the faster or more easily attracted this nucleophile is to this electron-deficient carbon atom. On the other hand, the second point that will be discussed is the bond enthalpy, or the strength of the carbon-halogen bond, because this reaction involves the attack of the nucleophile as well as the cleavage or breaking heterolytic fission of the carbon-halogen bond. Thus, two factors play a role here, which is the speed at which the nucleophile attacks, or the ease with which the nucleophile attacks this partially positive carbon, as well as the strength of this bond in terms of breaking this bond. Thus, one of these factors is more dominant over the other and dominates in terms of affecting the rate of the reaction. I'll explore both in this point. Thus, let's explore the polarity of the carbon-halogen bond. As you move up group 17, as seen here, iodine, bromine, chlorine, fluorine, the electronegativity increases. Thus, the carbon atom bonded to the halogen becomes more electron deficient and thus more vulnerable to nucleophilic attack, as I stated previously. Thus, the rate is expected to increase as you move up group 17. On the other hand, for the strength of the halogen, as you go down group 17, the atomic radius of the halogen increases, and thus the bond length increases as fluorine has the smallest radius, chlorine has a larger atomic radius, bromine has an even larger atomic radius, and iodine has the largest atomic radius. Thus, as you move down group 17, the carbon-halogen bond length would increase, and thus its bond strength would decrease, becoming more easily broken, as stated here, and thus a faster rate of reaction would occur. This factor here, the strength of the carbon-halogen bond, dominates the outcome and thus has a higher magnitude on the effect of the rate of the reaction. I missed the word higher here. It has a higher magnitude on the effect of the rate of the reaction. Thus, in an exam, if you were to answer a question regarding the identity of the halogen, you should discuss it in terms of the strength of the carbon-halogen bond and not the electronegativities. Since both of these contradict one another, the polarity of the carbon-halogen bond, as we move up group 17, the rate increases, rate of nucleophilic substitution reaction increases. On the other hand, if you consider the carbon-halogen bond strength, as you move down the group, the rate of reaction increases, but this factor dominates over the rate of reaction. And thus you would use the strength of the carbon-halogen to explain the increase in rate in an exam as you move down the group. Since a good example at this point to cover regarding the first 2 points we covered, which is whether it's a primary or secondary tertiary halogenoalkane, and the identity of the leaving group, would be as follows, and this is a very common multiple choice question in paper 1 exams. Thus they would ask, which of the following molecules would exhibit the fastest rate of reaction with sodium hydroxide, OH, or the hydroxide ion being the nucleophile that will attack the halogenoalkane. Thus, I would start by eliminating in terms of the identity of the halogen. As we move down group 17, the rate of nucleophilic substitution increases due to the weakening of the carbon-halogen bond strength, and thus iodine is the lowest in group 17, which allows me to eliminate the chlorines, the halogenoalkanes containing the chlorine groups, chlorine leaving groups. Now I'm left with whether this halogenoalkane is primary or tertiary. If you check this one, A, this is a primary halogenoalkane in which it's a straight chain halogenoalkane that has CH3, CH2, CH2, CH2 bonded with an iodine group. Thus, this is a primary halogenoalkane. On the other hand, this is we have a carbon atom here bonded to 3 methyl groups, which is bonded to a halogen, and thus this would be a tertiary halogenoalkane. The tertiary halogenoalkane undergoes a 2-step mechanism, which is an SN1 nucleophilic substitution mechanism, forming a carbocation intermediate, which requires less activation energy to form than in an SN2 mechanism, which is a 1-step mechanism that requires the formation of a transition state and thus has a higher activation energy. As I will note this here. This requires the formation of a transition state, while this requires the formation of a carbocation intermediate. And thus, the fastest rate of reaction would occur for this tertiary iodohalide group. So the answer would be C. The third point, or the third factor affecting the rate of reaction, is the identity of the nucleophile. In general, the nucleophile is an electron-rich species that is attracted to the electron-deficient carbon atom bonded to the halogen group, as stated previously. Thus, negatively charged nucleophiles would be attracted more easily to the deficient carbon atom than would a neutral one. Therefore, negatively charged nucleophiles react faster than neutral ones, since the negative ion attacks the electron-deficient carbon more easily than neutral nucleophiles. Therefore, if I were to compare H2O, a water molecule with a hydroxide ion bearing a negative charge, while H2O is a neutral molecule, the reaction with the hydroxide nucleophile would be a faster reaction. On the other hand, if I was to compare an ammonia molecule here with the cyanide ion bearing the negative charge while ammonia is neutral, the cyanide ion would exhibit a faster nucleophilic substitution rate of reaction. If you were to compare two negatively charged nucleophiles or two neutral nucleophiles, this would depend on the electronegativity of the atom bearing the lone pair in the nucleophile to which it's going to donate to the electron deficient carbon. I will clarify right here. Thus, the element holding the lone pair of electrons with the lower electronegativity value is a better nucleophile and thus reacts faster, since it can donate its lone pair of electrons more easily to form a dative bond. Thus, if I was to compare these two neutral molecules, the nitrogen here is the atom holding the lone pair, which it will donate, while in the water molecule, the oxygen is the one that's holding the lone pair in the nucleophile and which will donate its lone pair of electrons. Thus, if we were to compare the electronegativities of both the nitrogen and oxygen atom as we move across period 2, we know that electronegativity increases and thus oxygen has the higher electronegativity in comparison with nitrogen. Therefore, the nitrogen atom would more easily donate its pair of electrons to the electron deficient carbon in the carbon halogen bond, and thus would undergo a faster rate of reaction. On the other hand, if we compare these two negatively charged nucleophiles, the hydroxide ion and the cyanide ion, in the cyanide ion, it's the least both carbon and nitrogen are bearing a lone pair of electrons which they can donate, but the carbon is the atom that will donate its lone pair of electrons because it has the lower electronegativity as seen here. It has a lower electronegativity than nitrogen. Thus, I will be comparing the carbon's electronegativity value with the oxygen's electronegativity value in the hydroxide ion. As we can see here, the oxygen once again has a higher electronegativity value than the carbon atom in the cyanide, and thus the carbon in the cyanide nucleophile would donate its pair of electrons faster or more easily to form a dative bond with the electron deficient carbon, and thus would exhibit a faster rate of reaction. The last factor affecting the rate of nucleophilic substitution reactions is the choice of solvent. At this point, I would like to define what a polar aprotic solvent is and what a polar protic solvent is. A polar aprotic solvent is a solvent in which the molecules do not contain OH or NH bonds and thus cannot form hydrogen bonds. Therefore, it's polar and thus contains dipoles, but that are they're not as strong as those dipoles present in molecules that can form hydrogen bonds. This is a very important note to make note of at this point. On the other hand, a polar protic solvent is a solvent in which the molecules contain OH or NH bonds and thus are capable of hydrogen bonding. They won't actually form hydrogen bonds, but it's we state I'm missing a beat. We state that they can form hydrogen bonds just to note that they are very strong dipoles, since the electronegativity difference between the OH and the NH atoms in these bonds is very high, and thus they have very strong dipoles. Thus, polar protic solvents that are capable of hydrogen bonding have very strong dipoles. On the other hand, polar aprotic solvents do not contain OH or NH bonds and thus are not capable of hydrogen bonding and do not have very strong dipoles in comparison with those that contain NH or OH bonds. Examples of polar aprotic solvents from the homologous series we've learned so far are aldehydes, ketones, ethers, esters, and nitriles. None of these homologous series or functional groups contain an NH or an OH bond. On the other hand, examples of polar protic solvents would be carboxylic acids, which contain an OH bond, alcohols which contain an OH bond, as well as an amine group which contain an H bond. The SN2 mechanism which is a one-step mechanism and requires the formation of a transition state, the best choice of solvent for such a mechanism would be a polar aprotic solvent. It's a one-step polar aprotic solvent. Which have no hydrogen bonding and do not and thus do not have very strong dipoles and cannot form hydrogen bonds. It is important to note in an SN2 mechanism, which is a one-step mechanism as stated in my previous videos, that both the halogenoalkane and the nucleophile, which in my previous examples was a hydroxide ion nucleophile, which is capable of hydrogen bonding, both react in the slow rate determining step of the reaction. Thus, any change in terms of the stability of these reactants, let's say the reacting in the rate determining step, would affect the rate of reaction because they would speed up or increase the rate or decrease the rate of the rate determining step and affecting the overall rate of the reaction. Thus, if one were to use polar protic solvents for an SN2 mechanism in which the nucleophile is reacting in the rate determining step, the polar protic solvents would be capable of hydrogen bonding with the nucleophile and solvate them effectively via hydrogen bonds, and thus increasing their stability or lowering their energy state and decreasing the rate of the reaction. Since the hydroxide nucleophile is stable and does not really have a need in terms of attacking or cannot attack the electron deficient carbon, the carbon halogen bond, easily, since it's now solvated and it's in a lower energy state. On the other hand, if polar aprotic solvents are used, these solvents do not solvate, as stated here, these solvents do not contain hydrogen bonding and would not solvate the nucleophile effectively via hydrogen bonds. Thus, the unsolvated nucleophile would have a higher energy state, increasing the rate of the reaction. I'm just going to erase this here. The unsolvated nucleophile thus has a higher energy state and thus increases the rate of the reaction. This can be clearly displayed using an enthalpy level or energy level diagram for an SN1, for an SN2 mechanism, excuse me. I'm going to state this here. This is an energy level profile for an SN2 mechanism. This is for an SN2 mechanism, which occurs in one step, in which the reactants here are both the halogenoalkane and the nucleophile in both these examples, while the product here are the substituted products, and this point here is the formation of the transition state. As you can see here, if one were to choose a protic solvent capable of hydrogen bonding and thus effective at solvating the nucleophile, this would increase the stability of the nucleophile and lower their energy or potential energy in the energy level profile, and thus the activation energy required to form the transition state would be this much. This is when using an aprotic solvent, and this is my solvated nucleophile along with the halogenoalkane here. On the other hand, if you use a polar aprotic solvent that is not effective at solvating the nucleophile would have a higher energy state and would be a bit unstable over here. It has a higher energy state, and thus the activation energy would be lowered down to this much. And thus carried out at the same reaction, the reaction involving the polar aprotic solvent would occur at a faster rate, since the formation of the transition state requires a lower amount of energy, since the nucleophile is already in a higher energy state. As for an SN1 mechanism, the best choice of solvent for an SN1 mechanism would be a polar protic solvent that is capable of hydrogen bonding. And thus has strong dipoles that are effective in stabilizing the carbocation intermediate formed in the rate determining step by desolvation involving ion dipole interactions. I'm going to elaborate on this point. An SN1 mechanism involves a two-step mechanism. The first step being the slow step, in which the halogenoalkane reacts. It's a unimolecular rate determining step. The halogenoalkane undergoes heterolytic fission to form the carbocation intermediate, which reacts in the second fast step with the nucleophile, hydroxide nucleophile, which is the fast step, as stated in my previous videos. Any solvent that can stabilize the carbocation intermediate would favor its formation, and thus would lower the activation energy of the first rate determining step, thus allowing it to occur or form the carbocation intermediate more easily or at a faster rate at that given temperature. Thus, I've stated here, stabilizing the carbocation intermediate lowers the activation energy of the slow step. I'm going to state here the rate determining step. Oh, sorry. Choose the same colors. The rate determining step, favoring the formation of the carbocation intermediate and thus increasing the rate of reaction. Once again, energy level profiles for an SN1 mechanism would clarify this point. As seen here, this energy level profile is for an SN1 mechanism, which is a two-step mechanism as seen here. This is my reactance energy, and this is the products, final products. But it's a two-step mechanism which involves the first activation energy required to form the transition states here, which is the carbocation intermediate, and the second step, which has the lower activation energy required to form the product. Thus, the activation energy for the first step would be this much in terms of the use of a protic solvent, while in the second one would be this, and the use of a polar aprotic solvent would be this much, from the red line down to the reactants. And the second step would be measured from the transition state of the second step to the intermediate. Thus, the second step has a lower activation energy. Whether we use a polar protic or polar aprotic solvent, it has a lower activation energy than the first rate determining step, and thus the second step is the fast step. Although the nucleophile would be effective in at solvating the nucleophile in the second step, reacting in the second step, but the second step is the fast step. Thus, it won't affect the rate of the reaction because it occurs after the rate determining step. But any factor affecting the rate determining step would increase or decrease the rate of a reaction. Thus, as you can see here, if one were to use a polar aprotic solvent that is not effective at stabilizing the carbocation intermediate, the carbocation intermediate would have a higher energy state, and thus the activation energy required to form or the activation energy required for this reaction to occur to form the carbocation intermediate would be very high, as I will color code in red here. This is the activation energy required for the use when using a polar aprotic solvent. On the other hand, if one were to use a protic solvent that is effective at stabilizing the carbocation intermediate, since it has strong dipoles and thus can solvate the carbocation intermediate via ion and dipole interactions, the stability of the carbocation would increase, and thus its energy state would decrease over here, and thus the activation energy required to form it would be lowered, as I will note here with this blue line. This is the activation energy required to form the carbocation intermediate when using a protic solvent. And thus, if both reactions were carried at the same temperature, the polar protic solvent would allow the nucleophilic substitution or SN1 mechanism to occur at a faster rate than when using a polar aprotic solvent. I would guess at this point this should cover all the factors affecting rates of nucleophilic substitution, but I've noted here that from what we learned so far, the fastest rate of nucleophilic substitution reaction would be with a tertiary halogenoalkane, since it undergoes SN1 mechanism, forming a carbocation intermediate, which has a lower activation energy than the transition state, and choosing an iodoalkane or a halogenoalkane containing an iodine, since the carbon-halogen bond length would be lower. The bond strength would be low and thus would break easily, as stated in the second factor in this video, and the use of polar protic solvents, thus to increase the stability of the carbocation that forms in an SN1 mechanism for a tertiary halogenoalkane. Thus, a tertiary iodoalkanes in polar protic solvents would have the fastest rates of reactions. Thank you for watching.